All right, welcome everyone. You are at the May Data Science DC meetup, so hopefully you're in the right place. If not, maybe you'll stick around and learn something anyways. Today I have Jules Damji with me, and we're going to be learning about scaling and distributing Python and ML applications with Ray, so we're looking forward to that. Just before we kick things off, I want to tell you a little about who we are, who's putting this on today. Data Community DC is a nonprofit organization that has about close to a dozen meetups under its umbrella, including some of the ones that you see here. So check out datacommunitydc.org to find out about other meetups that are going on. Some of these we're trying to get going in person here soon. We're doing a hybrid of in-person and online, so just trying to work out all the kinks around that. If you are in the DC area and you have space that could be good for a meetup and would be interested in hosting us, please do share that in the chat or contact one of us. We'll have our contact information here in just a moment. So we have a number of sponsors who help keep these Zoom lights on and give us food and drinks when we are in person. So we appreciate both Prefect and ATA, who are our title sponsors for 2022, for making that possible. Give them a check out if you're in the industry. And if you want to contact any of us here at Data Science DC, Janet, myself, and Tommy and Chris are available. So please do message any of us here at our email addresses, or you can reach us on Twitter at the Twitter handles that are also listed here, or just hit us up in Slack in the chat. We do have a code of conduct here. In short, let's be nice to everyone. And longer, I'll give you a second or two to read it. But just know that we do take treating everyone with respect seriously. We also have a diversity statement here. We do like to see a diverse group of speakers, and we encourage all kinds of folks from different walks of life to please do volunteer to speak. We want to make sure that we have a diverse speaker profile that matches the diversity of our audience and our larger community. So do please hold us to that and make sure that we have diversity in what we do. Next up, our next meetup is going to be January 14th. Tommy, this is you here giving this talk. So we're going to be working on with LDA for transfer learning. And it may not be up on Meetup just yet. We're trying to finalize if we're going to have an ability to do it in person and online. We're looking at doing a hybrid there. I think that is probably going to work out, but we just need to nail down the space on that. But keep an eye out and we will let you know what's happening. Give us a subscribe to our YouTube channel. Data Community DC is the end of the URL there, so check that out. We'll put that in the chat here in a bit too. And also invite you to join us on Slack. We have a DSDC members channel there where you can keep the conversation going after the meetup ends. Any announcements from the community? Any upcoming events you want to chat about? Anyone looking for a position, hiring, anything like that? Go ahead and put that in the chat now, and we will make sure to give a shout out to that. Will Angel says there's a DataViz DC event on Thursday. Do check that out. DataViz DC has great events. You can find out all about that one in the Slack if you jump on over to the Slack, or we can also get a link to that meetup there. That's what DataViz DC. There you go. Thank you, Will. DataViz DC is one of those groups that's under the Data Community DC umbrella. Any other community announcements? Going once, going twice, and 3 times. All right, sold. All right, with that, I will turn it over to Jules, and we will look forward to hearing about Ray.
Okay. Well, let me go ahead and share my screen and make sure that you guys can see my bold head.
Looks good.
And let me just bring it full screen. Are we good?
All good.
All right. Well, thanks a lot, Jeff, and thanks a lot for telling me really to invite me. Great to see such a vibrant community here in DC. DC holds a very special place to me. I went to school at Johns Hopkins University, spent 2.5 years getting cooked in the summer. So I'm always delighted to be back. And I was just telling Jeff, hey, if you guys have an event next time, let me know. I do want to come in. So delighted to be invited to share how do you actually scale AI and machine workloads with Ray ecosystem? So I'm going to be talking about that today. A little bit about myself. I'm the lead developer advocate here at Ray team in Anyscale in San Francisco. And a little bit about myself. This is sort of a new role for me. I sort of currently am a lead developer advocate in Anyscale. Before that, I was heading developer advocacy at Databricks for about 7 years and ended up writing a book on learning Apache Spark. And then prior to that, I was leading the advocacy group at Hortonworks. And before that, held many sort of different positions from very early on at Sun Microsystems, where I was there for almost about 10 years, and then went to Netscape and at home. And so I've sort of seen the industry grow from desktop to mainframes to all the way to laptops. So it's been actually a good journey. And this is sort of a good transition for me to sort of share the knowledge that I've garnered over the period of years. So that's who am I. And the company I work for are the original creators of Ray, which I'm going to talk about today at different angles and different levels of what Ray is all about. And what we do is we provide a managed service, just like any other open source project. There is a company behind that actually gives the managed service in the public cloud. And our goal and our mission really in life is that distributed computing, we believe that is really the future today, especially as we're entering what I would call the zeitgeist of ML and AI, and distributed computing has become a necessity. And so we want to make sure that the platform that we provide, the framework that we provide, the APIs that we provide to developers is a lot easier to do. We want to make distributed computing simple. That sort of is our moonshot vision. And so today's agenda is I'm going to talk about all these different aspects of Ray, but I'm going to start with the origins of Ray, what and why Ray, what actually motivated the original creators of Ray to create this. So I'm going to start at 20,000 feet. I'm going to go down to 10,000 feet, and I'm going to go down to 100 level feet where we actually start looking at some code. And I'm going to talk about some of the libraries that people actually use to scale the machine learning workloads. In particular, Ray Tune is an important library where you tune your hyperparameters. There are other libraries available, but it would take me about three different meetups to actually explain the entire ecosystem. So I'm going to stick with Ray Tune today. And I'm going to do a demo where I'll show how you actually scale your machine learning load using 3 different workloads, the tuning, the hyperparameter training, and then inference. And then I'll answer any questions that I have. I'll also try to pose for questions in between sections. So if there's something that you feel that wasn't clear or you want some more elaboration, I'll be more than happy to engage. So, why Ray? And I think that's a question that a lot of people actually ask, why you actually need yet another distributed system framework. Aren't there any enough of those out there? There were actually 3 sort of industries trends when the original creators of Ray were working at UC Berkeley in the Rice Lab, which is a popular research lab in UC Berkeley, from where Apache Spark emerged and Mesos emerged and Caffe emerged and all these big products and open source software products emerged. They were looking at the industry, how trends are actually happening. And one of the things is that machine learning is actually becoming very pervasive in today's domain. As I said, we're entering an era where ML has become like a normal thing for us. And as a result of that, it used to be that distributed machine learning was a niche thing. People sort of, very, very well versed in distributed system would only write machine learning program. It was like a norm. I mean, it was more of an exception. But today, distributed machine learning is actually a necessity because everybody actually are writing distributed systems. We work in clouds. We do write distributed system. We don't know, but that's what we're actually doing with. And then finally, the other thing was that Python, as you know, has become the default language of data science and machine learning. And so any APIs that you actually provide to the developers, they have to have Python bindings because it is by default the de facto language. So those were sort of the three trends that actually led to the emergence of this particular new framework from RiceLab, which was the research wing in the UC Berkeley. And just to give you sort of a high level view, we know that AI applications across the industries have really sort of pervaded themselves. And these applications where people actually build models require a fair amount of compute time, right? From AI finances, where you write trading systems, where you're actually doing anomaly detection, where you're actually doing fraud detection, to smart transportation with computer vision and all that. All these industries are building very sophisticated models that sometimes take a lot of compute power to actually do that. And you can't really do that on a single machine. You actually have to do that over a distributed system. And these are not small models, the weights and the parameters that you actually deal in billions of parameters. So this has actually sort of necessitated a need to actually have a distributed system that can actually compute at massive scale. And if you look at this particular diagram from OpenAI a couple of years ago, you can actually see that today's language models require a fair amount of petaflops to actually train them, and it can take weeks to months to days just to do that. And the amount of the amount of parameters and the complexity and the compute power needed by these parameters sort of increase exponentially compared to the CPU power that you have. And so there is this compute demand supply problem out there where the demand is so high, where the current infrastructure cannot actually do that. Even though we have accelerators, right? You hear about GPUs, you hear about NVIDIA GPUs, and you hear about all these other GPUs and TPUs. They address a part of the problem, but they still actually have to be scaled over. And so there's still this particular gap that actually exists. And so people have to somehow figure out what's the best way to do that. And the researchers at UC Berkeley at RiceLab figured out that one way to do that obviously would be to massive scale in a very serverless manner, where you take your particular application and you just write it across a distributed system. And that was the only way you can actually do it, where you can actually distribute your parallel task, or you distribute your training, or you distribute your training across, or inference across all these different clusters with different accelerators. So that was trend number 2, that people actually found out that this is actually what's happening. And the third is obviously obvious, as I mentioned and I pointed out. I was just talking to Jeff. If you've been to PyCon, you can actually see the massive gathering of people coming over there, where it's, Python is a growing programming language, and it is by default become a data science and a machine learning program for really 2 simple reasons. One, right, most of the data scientists today are working on all these libraries available at their disposal to do their scientific computing, to do their data analysis, to work with data frames and all that. And if you're working in the deep learning and ML specific space, you got all these particular libraries that have Python bindings. And so any new framework that comes out, which is not written in Python, or at least it doesn't provide the Python API, would probably be on the losing streak of it. And so those were the 3 kind of trends that really led to the emergence of Ray as a distributed framework to scale your machine learning workloads, because we are forced, or we can actually support all these libraries as part of the ecosystem. And so what are the origins of Ray? I think it's important when you talk about an open source project, which is really sort of changing the paradigm of how you actually distribute code, you have to figure out what the origins were, where it actually emerged it. And the emergence of Ray are no different from how some of the innovations that actually emerged out of UC Berkeley's MLflow, where about in 2009, Professor Ian Stoica, who also happens to be the co-founder of Databricks. When I started very early years at Databricks, he was one of the guys, along with other 4 researchers who actually had finished the PhD at MLflow. He was also leading the efforts of MLflow. And David Patterson is one of the head of the ICC computer department at UC Berkeley. They sort of released this particular paper in 2009, which was very an opinionated paper about saying, what is the Berkeley's views of serverless computing? Where are we actually heading with serverless computing? Even though at that time, AWS had already had their AWS cloud, but this was a way to sort of formalize how serverless computing will work. What are some of the design patterns in the cloud computing? And it actually created quite a bit of buzz in the academic and also in the industry, where more than 17 different citations in paper that were used. And that sort of whole idea about Berkeley vision of serverless computing played quite a big role in the emergence of Archie Spark in the Databricks as a company. And ironically, 10 years after that, there was a new paper that they actually published in 2029, which was a different spin on the same paper, but they claimed that this is the new Berkeley vision of serverless computing. And there was a postgraduate student over there by the name of Eric Jonas, who is now a professor of computer science at the University of Chicago, where he was studying all the PhD students at Rice Lab, where they were building all this distributed system, and the graduate students were not using Spark to do the ML, right? They were actually sort of writing things on the desktop and then using the serverless computing in either AWS or somewhere else to ship that particular code, and then let sort of the compute and the separation of storage sort of independently do the computation for them. The whole idea behind that was they can take an abstraction of the code that actually have and distribute it across the cluster and let the cluster figure out how much resources we actually need. And that sort of findings in that particular paper in 2019 really fit into the whole idea of what Ray is, right? Why Ray became sort of an important part in this collective research. So I think those two fundamental trends, along with what was happening in industry and what was happening in the academia, sort of merged together. And that was sort of a good input into the emergence of what Ray is all about. And if you actually haven't read this particular paper by these researchers at Rice Lab, I urge you, because you sort of get an idea of the opinionated way of how Berkeley was looking at the future of serverless computing. It was very prescient at that time, both in 2009 and also in 10 years after that, in 2017, which sort of led to the emergence of serverless computing and the patterns involved in serverless computing that actually led to the current rise of Ray. So that was sort of the origins of Ray, right? MLflow was one of the first earlier sort of crucible of innovation that created Spark and Apache Spark and Mesos, and then MLflow was shut down. Well, MLflow was succeeded by Rice Lab, headed by Professor Ian Stoiker, who also happens to be founder of Anyscale, and Ray sort of emerged out of that. And there are the other sort of projects under UC Berkeley, which feed into the open source ecosystem very well. So those were sort of the origins of Ray. And so what is Ray now? I've talked about the origin, how it actually came out to be, and what is the origin of Ray? We can think of it, it's a very simple sort of general library for distributed computing, right? The important thing is that it's simple, that gives you abstractions to write primitives, so you can actually write your distributed application. It is general in the sense that it's not based on any particular abstraction of data structure, right? For example, Dask is based on data frames, Spark is based on data frames, a distributed data set. So Ray is not the same. Ray is sort of built on the abstractions that you can actually use to build any distributed system you want. So it's very general in that particular way. And it is a collection of Python libraries for scaling your ML. So there's some native libraries which are built on top of Ray that allow you to do your machine learning workloads. You can actually scale them across this particular cluster. And finally, the important thing is that you can actually run this thing on your laptop if you actually wanted that, because that's what those graduate students were doing. They were actually working on the laptop and scale it to your cloud, run it on Kubernetes, or you can run it on premise. And that was the important part of it. And you can think of Ray as a layered cake of functionality, right? Capabilities for all that. And so if I had to give you this architecture diagram, you can actually think of it that Ray at the bottom is your infrastructure where you can run in anywhere, in any of the public clouds. The bottom part, the middle part is really the core. And the core is where we actually Ray provides you this primitive abstractions, these APIs, which are the ethos and the philosophy of Ray. It will give you the primitives and you worry about just writing those using those primitives and APIs to write your distributed application. We will take care of the scaling, we'll take care of the scheduling, we'll take care of all the heartbeat. You don't have to reason about it. And then on top of that, you sort of build these native libraries, which are on the left-hand side, you can actually see, which are some of the workloads that most of the data scientists and machine learning people actually use those. Or you can actually have third-party integrations that actually run on top of Ray. And if you are one of those guys who actually don't do anything with ML or deep learning, but you just want to write a distributed application, you can use those primitives and write your own library to run as a part of Ray. So think of Ray as a computer starter that gives you primitive abstractions to write high-level libraries that can actually scale across horizontally in your cluster. So that's what I mean by layered functionality of compute, that Ray facilitates that. And it comes with this rich ecosystem of scaling your workloads, right? So if I wanted to do some pre-data processing for transformation of data before I feed into my ML, I can actually use my Ray datasets to do that. I can use Dask on Ray to be able to do that. I can use Modem, but I can use Mars for my tensors. So that sort of comes natively straight out of the box. If I wanted to do distributed training, I can actually use Ray Train. And I can use any of these three libraries, which are very popular for doing distributed training, PyTorch, Hugging Face, if I actually want to use Hortonworks, TensorFlow, and so on and so forth. If I wanted to use serving, if I have models which are served, which are sitting, say, on a model registry, I can load them and then serve them using serve. And then hyperparameter tuning is an important part of your machine learning workload. Any data scientist who's on board today will say that half of the time they sort of tune their models with different config space to make sure that they get the best optimized parameter for the model, and then use that model to do the inference. And if you are in the gaming industry, or if you're building recommendation systems, or if you're doing simulations in the real world, reinforcement learning is one of the popular libraries that allows you to build your reinforcement application. So that's sort of are the 3 or 4 libraries that allow you to actually do that. And so that's, these are some of the companies which actually are using Ray at a massive scale, right? Uber and Amazon and Ant Group, and all these are also contributors as well. And so there are a lot of people actually using Ray, both as part of the Anyscale, also they're using Ray on their own cloud or the prem. So that sort of gives you at a very high level what Ray is about, what the origins are, where it actually came from. And I'll just pause here if there's any questions that people actually have. If not, I'll just go on to the next one.
I can just ask a quick question here. People are thinking about something. You mentioned Dask is doing some similar things in some areas. Majid's kind of commenting on this kind of similar. Lower level Dask isn't really built on a data structure. That's exactly where I was going there too, Majid. There are these Dask bags and futures and delayed, which are kind of more primitive type things. So it looks like those can be used with Ray. It looks like there's a Dask Ray kind of combination. I was wondering if you could just talk about that a little bit.
Yes, there is a way you can actually run Ray on Dask. And if you look at how Dask is actually built, right, the way the Dask sort of uses a central scheduler whereby you create all these Dask tasks, and when you're done the task, you actually give it to the Dask scheduler to actually do that. How Ray fits in is that there is a way within Dask where you can actually provide dask.config and what scheduler you actually want to use, right? So now you can actually use a dynamic scheduler such as Ray or any other scheduler that you actually have. And once you actually do that Ray, what happens at that point is that Dask will go in and create all the tasks for your bags and data frames using the Dask API. So you will create your static DAG graph statically, and then it will fan it out to Ray to do the execution in parallel. And that's where the Ray and Dask comes in. And the integration is very simple. It's just one line of code in the Ray.conf in the Dask.config scheduler equal to Ray, and you run with that. Does that answer your question?
Yeah, thank you.
Okay. All right, so now I'm going to sort of drop down a little bit from this high level of the origins and the Ray architecture. And, those of you who are working on distributed system, this particular anatomy of a Ray cluster is no different, right? You've seen this before. The Spark cluster looks like that, Mesos cluster looks like that. There are some distinguishing characteristics, which I'll talk about that. So each cluster node actually has similar components and similar processes running, except for the head node. We just call it head node because it's got a driver and a central GCS store, which is a meta store that contains the state of who is doing what and what the resources are available and what code is running where. You can think of it as like the control store of everything, and we have a driver. And then each node actually has a worker. Now we just happen to call that the head node. The driver and the control store can run anywhere, but we just call it the head node for just convenience and convention. The workers are the Python processes which are bound to a particular core. So if you have 12 cores or 24 cores on a machine, you will have these worker processes on a worker node. And there is one process called Raylet, which is 2 threads running. One is a scheduler and one is an object store. And these Raylets sort of work together to create this very unique way of how Ray does the distributed scheduling and how it actually has what we call a distributed object store, right? And this is quite unique to Ray. No other distributed system so far actually has that. So at any one point, everybody knows who is executing what particular task, and they communicate that using GCRPC. So you can think of it as like a distributed schedule. There's no central point of command that distributes the task. It's actually done through this coordination and collaboration across the entire cluster. And that's something quite unique to Ray. And the object store gives a lot of performance benefits to processes which are running on the same worker node because of the Plasma shared Apache store. So if you have data that's running on the same node, the Plasma shared memory actually gives you 0 copy benefit for all the data that are coming in. So processor can actually, you don't have to copy the data over. They can just go straight to the shared memory and get the data. So that sort of is how Ray sort of shared across, the object store is shared across the different cluster. And if I look at the more individual tasks, you've got the driver, which I said driver sort of is the main task that would talk to the Raylet to say, go ahead and execute this particular task. And the Raylet will try to figure out how do I actually schedule tasks? What are the requirements? Do I need CPU? Do I need GPUs? All these are sort of managed by the Raylet to schedule the task. The Raylet talks to each other and broadcasts their resources available, so everybody knows who has the GPUs and who has the CPUs and what tasks are running there. So you can actually make an intelligent decision to say, okay, I'm going to schedule this task over there because the data that you actually need is there. So there's some sort of a data locality. But at the same time, everything is actually also stored in the global store, whereby the global store has the ability to broadcast it all to the Raylets. So every Raylet actually has a picture of what other Raylets are doing and what resources are available. They can actually make an intelligent decision when it's actually scheduling things. So that's sort of at a little low level how things happen behind the scenes when you execute a particular primitive. And we'll look at some code, what happens there. So that's sort of another high level. And so next thing I want to talk about is the primitives I talked about. Remember when I was giving you the layered structure of Spark, God forbid, of Ray. The underlying philosophy of Ray was to provide these high-level distributed design patterns, and those are expressed in terms of primitives. And though you use those primitives to take your existing functions that you have or your existing classes that you have and convert them into distributed manner without really understanding the knowledge, without having the knowledge of how they actually done that, you don't have to reason about it. And there are certain design patterns that Ray provides and encourage that people actually use it. And obviously there are APIs associated with that. So let's look at that. Now, the design patterns are not something new, right? These design patterns exist in programming languages. All of us who are software engineers and data scientists and ML engineers have gone through these design patterns. And if you have read this particular book by the Gang of Four, that's where the whole idea about design patterns came about, came up into being, and it sort of infiltrated into our programming languages. And so Ray provides you with three design patterns that you can actually use. One is called Ray parallel tasks. And those are functions or stateless units of execution that you can actually take and then schedule it on any of the node that you get. You don't have to schedule it, it schedules it for itself. It runs it, it computes that. If it needs more resources, it'll automatically be created for you, and then it returns you the tasks back. there's this notion of what we call ray objects, and ray objects are like features. And those of who are sort of Java or Scala programmers or Python programmers, there's this notion of features whereby you create a particular feature, and at some point in time, asynchronously, you can query that particular feature to get the actual computed value. If not, then you either block on it or some way that you can actually inquire the state of it. And these are stored in what we call plasma stored. And I talked about the plasma store, the Apache plasma store, which is part of the shared memory of each and every node. And then that's sort of shared across the entire cluster. And this sort of enables for you to do a lot of things asynchronously because you don't block on anything. You schedule a particular task. You could be doing the class for a while. You get an object reference back. And at some point in the future, you can actually invoke and inquire the state of that particular feature. And the last bit is the ray actors. And those of you who are familiar with Erlang actor or Akka actors, the idea is very similar. It allows you to create what we call stateful services in a cluster, and they manage a particular state. And those are bound to a particular node in the cluster, and you can actually do message passing and all that. And in all of these, you're not having to worry about, oh, am I going to create a socket point, or I'm going to have to worry about, where this particular thing is scheduled. That you don't have to worry about. All that reasoning is actually taking care of that. So let's look at some code, how this translates itself, right? So the function, a Python function is a task. They may convert into a task and be scheduled on a node. A class is an actor, which is a stateful service that can be scheduled to run on a node. And an object is a result of either something that executed on a particular node by a function, or a method within a function that returns a particular value. And what you get back is not the value itself, but you get an object reference to a pointer in the object store, which can later be fetched by using one of the ray primitives called get. So let's look at some code, right? So here I have a function called read array, and all it does, it takes a NumPy array, does some computation and returns you some value, whatever that value is. And all I have to do to convert that into a remote task, I just annotate that with the ray decorator by saying ray.remote. And now that particular function will be converted into a ray task, which will run on a particular cluster. Then I have another function called ray.remote, which is called add, that takes in two arguments, two NumPy arrays, and I just add them together, right? And I just return it back. And then in my main program, if I want to execute that ray task, all I do is I give the name of the function, read.array, and I say d.array remote, and give the argument. And at this point now, you're executing that in the remote fact. It returns you an ID, which is a reference, right? So anything in blue you actually see is the object reference you actually have. And the same thing with read array 2. That's going to execute another file somewhere else, and it's going to return you a reference. And then I do array.remote. Now note that when I do array.remote add, I'm not sending the values of A and B because I don't know what they are, right? I don't know what's being returned to me. All I'm sending is the reference that was returned to me by the remote task, which then will resolve in real time when the ray.remote is added and when the object reference are referenced to get the value, and then I get the value back of call ID. And at this point now, I can say array.get, which now will block at this point to make sure that all the other two tasks are finished and asynchronously. And if they're done, then you actually get the value back. So that sort of function on the left-hand side is your task. The function on the right, the code on the right-hand side is equivalent of taking an actor, taking a class that you have, which is Python, and converting that into an actor. And then that actor can now be stipulated or can be designed to say, okay, I'm going to run this on a 1 GPU because I need those resources, or I'll need 2 CPUs to run those resources. So you can actually specify the resource requirements that you have for that particular counter. So over here, I've created a particular class. I have a function called a local method called increment, and all it does, for simplicity and illustration, just returns the value. And in order to create an instance of that particular actor, all I do is use the class name and do a remote. Very simple API, very Pythonic, do a remote, and I get a handle back. And in order to invoke my function, all I do invoke the methods within that particular remote actor. I do cdown and create a remote, and I get those things back. So how that actually get translated is that on node 1, I'll have the first function being executed, which will read a particular array, right? A file which is either sitting in an S3 bucket or whatever location it is, and it's going to immediately return me an ID reference. The second one might be scheduled on a node 2, and it will read the file and return me a reference. This is all done dynamically. And I think the reason why it's that dynamically, because if you do in machine learning workloads, when you're doing hyperparameter tuning or when you're doing training, you can't really wait for a static graph to be computed and then wait for the scheduler to execute it. You want those trials to be run eagerly so that when you get the result back, you can say, okay, I'm going to drop this particular trial because I didn't get a good result. And so that way it's very important to get these execution of these DAGs dynamically rather than lazily. And so over here, I'm creating my dynamic task, and then I'm going to return back the ID for the add function. And then I'm just going to do a get on it, which will actually block until the value is actually available. So that's sort of, the code of tasks in API that gets translated. And so this is sort of how the actually graph is executed in the on the cluster. So I talked about the distributed object store. What does the object store actually mean? So this is the implementation of Apache Plasma, which actually uses the Plasma internal structure to store the array, so you can actually do a lot of fast copy internally. So if you have worker nodes or worker processes which are running on a particular node, and they have several tasks which are running, and they're actually creating some objects, and so each worker process, each node that actually creates an object is responsible to create the knowledge of its metadata. So I have the worker process that actually creates two variables, X and Y, which is actually stored in the shared memory. And then I have worker process, second process that actually creates the worker Z. Now, if a worker process needs a value Y, I don't have to copy from worker process 1 to worker process 2. I can just use the shared memory zero copy straight from the shared memory. So I don't have to actually do the IPC communication, or I don't have to use the bandwidth. So when you have data locality of this nature, the performance of these particular tasks which execute remotely is quite fruitful. And if your shared memory object store on that particular node does grow very fast, there is a way to actually spill it over, and it uses your normal eviction algorithms to figure out how to actually do the eviction. So that's sort of the nature of how distributed object store actually works quite efficiently in Ray. And the way you can think of it pictorially, if you're actually looking at some code, if you have a function called f and you compute a task that creates a value called x on node 2, it's going to put that in the shared memory as a value x. And then I have another function called g that's going to return a particular value. But note what happens over here is that when I send in the value of idx to g, it might schedule that function directly on the node 2, because it knows that it actually references a certain value which is actually stored over there. So it takes advantage of locality. So I wouldn't schedule the function f elsewhere. I would just schedule it on that particular node. And same thing with g. If g needs some data and I know the data exists on node 2, I'm going to schedule it over there. So that way there's not that much of data being passed between nodes. I'm just using shared memory for that. So this is a knowledge that's actually done, behind the scenes, but you don't have to worry about it. You're just writing your Python code as if you are writing everything that's running locally, but now things are actually running in a distributed manner, in a very seamless manner. If you look at this particular code, there's no socket creation. There is no need for you to understand, okay, where am I actually executing this? How am I going to get this particular data? All that is actually taken care of that. And that makes the attraction to Ray programmers to use these APIs quite seamlessly. So how does Raylet, I talked about Raylet, is how does it actually schedule tasks, right? How does it actually do that? And so it uses all the different policies. So one way it actually figures out that where I need to schedule a particular task, it uses what we call, I'm going to ask a particular Raylet to give me a list of particular node, because I have some requirements for, I need this particular task to execute on GPU, and I need this particular task to do another one on a CPU. So it will query its own Raylet to say, hey, can I actually, do I have resources? Do you have the resources for these things? And if you have them, give me the particular lease, right? And it gets a particular lease for a certain amount of milliseconds, and then it's going to communicate with that particular arraylet to execute that particular task. If for some reason that particular arraylet cannot satisfy the request, what it will do is that arraylet say, hey, I don't have the resources, but I know, Jeff is running this particular node. He actually has the resources. So why don't you just execute on his node? And so it gives a reference back to arraylet to say, go ahead and go to Jeff's node, and he has GPUs for you to actually execute that. And then it actually gets a lease from that. It asks Jeff's node to say, can I execute this particular task? And it actually does that. So these are, these are the way how it actually sort of schedule things mentally, but you don't have to worry about it. It's actually done underneath. So all this is actually done through, using gRPC. So it's quite efficient in its chatty mechanism. And then if you're scheduling, many tasks, it caches all the different leases that you actually have. So I don't have to, do this this lease asking protocol. I know exactly what particular lease was allocated to what particular node. So I know I'm just going to go directly to the particular worker and then schedule the task. So that's how sort of scheduling decisions are made behind you. So if I'm executing, thousands of tasks, and all the required the same thing, I can schedule them on the same node because I know that node actually has a lot of resources available. So that sort of gives you a whirlwind of the Ray APIs that sort of make the distributed writing application quite simple. Are there any questions at this point? I'm covered a lot.
Give people a second here to see if they put anything in there. I just put the definition of gRPC for anyone who's not familiar with that acronym, perhaps.
Yeah, it's a sort of Google version of gRPC, which is sort of based on protocol buffs, and protocol buffs are a way for you to sort of create a definition of what you're going to pass back and forth. And so you write a protocol buff, which is like an interface definition, say this is going to be an integer followed by a real followed by a string. And those of you who remember, maybe I'm dating myself, but those of you actually remember Sun Microsystems created this thing called NFS, which was a file server, and it had an XDR protocol, how we actually was exchanging data between each clients. And XDR was a way to say, this is my contract. I'm going to define this particular structure called my payload, and my payload will have an integer, which will be the first 2 bytes, and then I'll have a pointer, and then I'll have that. This is something very similar. So there are protobufs that allows you to create a data format, and then it actually uses the HTTP2 protocol to pass the data over. So this is what gRPC is. Any other question? Brilliant. So I'm going to shift your focus now to one of the Ray libraries, which a lot of data scientists and a lot of machine learning engineers actually use that, called Ray Tune. And as the name suggests, tune is something that you tune, right? You have a particular model that you want to build. You have a business objective that you want to finish. There's a certain metric that you actually want to make sure that the model gears towards. And so how do you actually do that, right? You create a particular model, you use a particular library, scikit-learn or XGBoost or PyTorch, and you start sort of tuning, you start playing around with different parameters to figure out, what's the best particular model. And that's where Ray Tune comes into being. So what is Ray Tune? I think Ray Tune, just like any other tuning libraries that some of you might be familiar, like Optuna, HyperOpt, is a way to tune your model so that you get the best model, the most efficient parameters that allows you to give you a prediction and give you a higher rate of accuracy. And it supports a large number of state-of-the-art algorithms that enable you to do your trials in massive parallelism, right? Because it actually runs on Ray, you can take advantage of this, creating trials in a parallel and then fanning it across the cluster and then bringing the results back and then trying the next trial, all this happening in very sort of orchestrated manner. And the APIs are very simple. And you have a choice, right? You have a choice. You can actually run Ray Tune on a single machine on your laptop, or you can run a single machine with multiple cores. If you actually have like an Apple laptop or Linux laptop that has 16 or 12 cores, all cores can actually be used to have separate trials, or you can run it across a cluster. And the APIs are very simple. And we'll look at one example that I'll show why it is a lot easier. And so it also saves a lot of time, because when you're doing tuning, you want to take care of the bad trials, because you don't want bad trials to be coupling up your CPU or taking up your CPU time, because you're not going to use that result of the trial is going to be bad. So one way to do that is to save the cost by early stopping the trials. And there are schedulers that you can actually use at RayTune that figures out, oh, this combination of the hyperparameter tuning is not good, so I'm just going to early stop and I'll go to the next one. So all that sort of is part of the RayTune. And so these are some of the search algorithms that RayTune actually provides. And it's very simple. You just say, I want to use the hyperparameter search algorithm to do my searching across my config space that I provided. And I'm going to use a scheduler that allows me to do either early stopping or ASHA stopping, or what they call, halving as I go along. So these are all these different algorithms that you actually support. So to use them, it's very simple. When you're actually using the Tune library, you provide the search algorithm you're going to use, and you're going to provide the compatible scheduler that you're going to use, and you just write your training function and you let the tune run. And we look at some examples both here and in the demo. Hopefully we have enough time for that. So, those of you who are not familiar, I'm sure most of you probably are familiar with how hyperparameters are, but just for the sake of recap, there's a distinction between hyperparameters and modal parameters, right? Hyperparameters are parameters that you specify before the training that will affect how the modal parameters will be computed and learned as you go through the different algorithms in your loss function and all that. So some examples for hyperparameter tuning would be, what will your network architecture look like? How many CNN layers would you have? How many dense layers you will have? What will the filters look like? What will be your learning rate? How deep is going to be your tree if you're using XGBoot? All these are parameters that you actually define ahead of time in your class constructor for the algorithm that you're going to use for your either scikit-learn or XGBoost or PyTorch or TensorFlow and all that. And the modal parameters, by contrast, are the ones which are actually learned during the training, which could be for regression, it could be regression parameters. For a network architecture, it could be the weights and the biases and all the filters and so on and so forth. So that's sort of just the general high-level idea of what hyperparameter tuning is and why you actually need them, because they affect what your modal parameters are going to be. And here's an example of, in your network structure, some of the hyperparameter tuning that you'll be most concerned about is the max pooling, the strides, the dense layer, how many dense layer you're going to have, what are going to be the initial layer, and so on and so forth. So these parameters over a period of time, or the config space gets really, really large. And for you to be able to sort of tune it in a more efficient manner, there are some challenges associated with that. And those challenges can be costly because it is time consuming, right? When you actually have a large config space on which you want to combine and try each and every combination, it does take quite a bit of time and is very costly. And so you want to make sure that the resources you consume are at a lower cost. And what are some of the strategies that you actually use? And you actually want to use a framework, or you want to use a library that is fault tolerant. In other words, that if you have 200 trials that you are running and it fails at 150, do I have to start all over again, or can I just start from where I left off? And is it elastic enough whereby if I'm running 200 parameters and I'm really exhausted and I only have flow cluster, do I have to now stop that, create new clusters, and then start running again? Or does it automatically scale? That's where a rig has the ability to auto scale that, where it figures out, oh, I actually need some more resources. I'm just going to go in and create more cluster, and it will schedule those. So I think these are the important challenges that any library that asserts itself that it's going to do hyperparameter scale should be able to meet those. And so how does RayTune address those challenges? Sort of it gives you, obviously, first the state-of-the-art algorithms which are sort of part of the selection process. As you saw in the documentation page I showed, you can actually choose the search algorithms and the associated schedulers that allow you to do all these different combinations, whereby you can do early stopping for certain trials that are going to cost you, which are not going to benefit. There's no merit on it. So I'm just going to, swamp it and kill it. And so there are three strategies that Ray Tune provides you with that you can actually play around. You can actually selectively use that. One is the exhaustive search, which is sort of brute force method. One is the Bayesian optimization that sort of builds on the previous trials. And the third one is sort of more advanced scheduling, which uses, state-of-the-art algorithms to do early stopping and successive halving as the trials get fan out. So let's just very briefly look at what I mean by those. Now, exhaustive search, most of you are familiar. If you're using scikit-learn, you probably have used grid search in your algorithm at some point, or you use a random search. And they're very good in parallelizing because they're easy to implement. You're going to have a different discrete combinations of your grid search, and you're going to create a parallel task, and you'll go ahead and execute them. Same thing with random search. You create a uniform search across your config space, and you'll go ahead and execute them. The problem with them, they're very inefficient because you don't know how the previous trial performed, so you can't really make a decision whether I should go with the next combination that actually has one of the other parameters. So you are sort of, exhaustively going through everything. For a small, parameter space, people use that. There's no problem, but there is a cost associated with it in the large config space. The second one is the Bayesian optimization, which sort of what it does is it actually uses the results of the previous trials to ascertain whether should I actually use my next trial, including some of the parameters that I used, because I know that the result that I got back wasn't very good. So it would selectively sort of from the previous results ascertain and figure out what the next trial was going to be. And there are popular libraries that actually use this particular mechanism, and it's inherently sequential. In other words, I have to run this in a sequential manner. There are some libraries who have implemented it in a parallel manner, for example, HyperOpt and Optuna and some of the other ones allow you. So if you look at how these operate, it uses sort of, the Gaussian process to figure out what are going to be the next set of trials. And over here, this figure in the blue says, these are the parameters that I have found out from the previous runs are good for us to do the next trial. The ones on the far right, on the red side, are the ones that I'm not going to use. So that's sort of one way of using Gaussian process to ascertain which are going to be the next trials that I'm going to use, right? And then finally, the more efficient one and the most common one is the advanced scheduling that you actually use that implements early stopping, right? So over here, you fan out a number of trials across your config space, and you use hyperparameter tuning with either Hyperband or Asha that use successive halving to say, okay, with these set of trials on rung 1 and rung 2, I know that it didn't do very well, so I'm gonna stop it. And I'm just gonna go to the next one. And then as it goes along the trial, the ones that are actually performing, it will continue doing it all the way to the end, right? So that's what the advanced scheduling is. So that sort of Ray Tune sort of gives you the ability to use any of these strategies that you actually want to field to tune your hyperparameter. And it's very simple, right? If you're writing code in hyperparameter, there's 3 steps, right? There's 3 very simple steps. First, you define your training function, and this is a training function which has your objective function that you're computing the loss against. In this case, I just have a dummy example. I have a CovNet that takes a certain config space for my network architecture. I have over epochs, I'm going to compute my loss, and I'm going to use that that's my training function. So if I wasn't using hyperparameter tuning, I would just use this particular function to train the model, get my loss, and then I'll just use that to predict. The second step is you define your config space. What are your hyperparameters you're going to run over? So over here, my alpha is my tune uniform from 0.1 to whatever the particular number is. So it's going to use that random search to do that. And then I want the number of samples that I want. And then I'm going to use the Asha scheduler. Like I said, you can actually define what scheduler you're going to use. I'm going to use my Optima to do the search. And then you just say tune.run and boom, off you go, right? And what happens is that this particular code underneath translates into a driver process that takes that particular run and then creates these worker processes. And the worker processes get a copy of your training function with each individual trial. So now you actually have a fan of all these trials which are running in parallel across the worker nodes, and they communicate across each other by reporting the metrics back to the orchestrator. So the orchestrator can say, if I'm using early stopping, or if I'm using successive halving using Asha, can I actually do an early stop and figure out what my next trial is going to be? And that's where the orchestrator determines, after it has got the results back, and then it's going to terminate that. It will launch a new trial instead of the old one. And then intermittently, there's a checkpoint, and this checkpoint could be a local directory, it could be something on the cloud. And so this gives you the fault tolerance. At some point, one of the worker processes dies. What do you do at this point? Do you actually start all over? No, you just load that particular checkpoint from the particular worker, and you will start restoring it, and it'll start working from that particular point on. And all the other processes are still running without affecting this particular worker process. And at some point, you're pretty much done, and you got your hyperparameter tuning available for you. So that sort of was the Ray Tune library. Any questions here?
I've heard it's become quite popular. It seems like a really nice setup.
Yeah, I mean, Ray Tune is one of the popular libraries if you're using Ray, because for two reasons. One is that if you come from, say, an Optuna background, or if you use hyperparameter Optima, you don't actually change your code. You just say, I'm just going to use that particular library to do my hyperparameter tuning if you actually want to do that. And so Ray provides you the framework to actually execute this particular training function. So your training function is any Python code that you just provide to Ray Tune in this particular code over here. And it's going, this is your training function, and it's going to go ahead and execute that particular function across all the different workers as Ray tasks or Ray actors, depending on whether it's a class or it's a function. There are two ways you can define. You can define a particular class, and you can actually define a training function as well.
Got a question here
Yeah.
from Suzanne Nichols. Are there particular ML types that work best with this?
Are there any particular ML types? What do you mean by types?
Like I imagine like certain supervised learning algorithms that work well, or some things that don't work as well.
Yeah. I mean, good question. I think any algorithm that actually requires you to tune your parameters, both supervised learning and unsupervised learning would do that. So for example, reinforcement learning, there's no notion of supervised learning. Right? Reinforcement learning has a policy, and the policy is based on, I'm going to tune my policy so that if I get a particular action, if I get a particular environment and I have my state, I'm going to determine what my next action is going to be. It's got nothing to do with supervised and unsupervised learning. So both supervised and unsupervised learning can actually be used for that. If I'm training my network, obviously supervised learning, but the features are not something that I'd sort of discovered as you go along. So yes, it is suitable for both supervised and unsupervised learning. And the reason I say that because RL is one branch of machine learning where you don't use sort of labels or anything like that. Mm-hmm. Suzanne, does that answer your question?
She also had a CNNs here, random forest, just as a way.
Yeah, random forest, any of these. I mean, XGBoost is one of the very popular library, and there is, when we get into demo, I'll actually show you how I'm using XGBoost to fan out the trees across. So yes, you can use that with XGBoost as well. So there's a drop-in replacement for scikit-learn as well. So if you're using scikit-learn on a single machine, but you want to use the grid search across, then you can use the Ray Tunes drop-in replacement to fan out your grid search across. So quickly, in the takeaways, I mean, I talked a lot about the takeaways. The distributed computing is really becoming a necessity because we are sort of entering in this particular phase. It's not a norm. It's not an exception. It's actually a norm. Ray's vision really is to make distributed computing very easy. You just write this particular APIs and not reason about all the scheduling and fault tolerance and the performance, all that supposedly taken care of by Ray. And you don't have to be a distributed programmer, right? I mean, in the early days, maybe Jeff and I probably are at the same age, but you had to write MPI programs. You had to really create a particular socket. You really had to understand all those things to write, distributed code. You don't have to do that. All that is sort of abstracted away. And the whole philosophy behind Ray is we provide you the abstraction, and you use those primitives to build the high-level application. So if you look at all the Ray native libraries which are built, they actually are built using all these primitives. And so when you do ray.run, as I showed you, the all this thing over here are all worker processes. All these are actors which actually run, and they all use the Ray primitives that I talked about, actors and classes, right? You are not writing those. Ray is doing it. You just execute a high-level API to go ahead and do that. Okay, how do you get started? Very easy. Go to your machine today. Just do pip install Ray. We have a meetup with the cadence of once a month. So if you're interested to find out, how the community is actually using Ray, please come and join us. We're actually having a meetup shortly next month we're going to talk about, for 3 speakers from the community is going to talk about Ray on Kubernetes. So that would be a good discussion with those who are interested to use Ray on Kubernetes. We have a Slack channel, media, come and join us. Join our GitHub discourse to have very lively discussions from the community as well. And we have a Ray Summit coming up pretty soon. This is going to be a first in-person Ray Summit. I'm the program chair, and so I invite you, if you actually want to come down to San Francisco and get away from DC, there's a Ray Meetup, 25%. There's an early discount along with that. Actually, we give you a good discount. So thank you very much. Let's stay in touch, and we have some time, so I'm going to give you a demo. Okay, so let's do that. So let me see if I can move these things around here. Brilliant. Okay, so this is my particular Jupyter notebook. What I'm going to demonstrate over here is 3 workloads that I talked about. One is training, and the other one is hyperparameter tuning, and then how can we use inferencing. And so the first thing I'm going to do is I'm going to have to run this particular small version of that on my laptop, which is something similar most ML and data scientists do. They actually will run something on a laptop. It works, it finds. Now I want to scale it to the cluster, so I'm going to run it on my cluster. So now we're going to see the difference between running it at scale on a local machine and then trying to do the same thing on a cluster and see the merits between the two, right? So I have my normal import statements. I have your classification algorithm that I'm using. I've got about 10 million rows, about 40 features that I'm going to classify, and I have 2 classes, right? The 2 features. And this is just some boiler code that creates my 3 different files that I'm going to use, right? So that's what I actually use. I'm going to use XGBoost, and XGBoost is a very popular tabular format. A lot of people actually have used it for both classification as well as using regression. So that's my training. Now you can see that I define my XGBoost parameters. This is going to be my regular XG parameter parameters that I'm going to use. I'll define my XGBoost D matrix, which is your internal data structure and how you put your NumPy arrays in there. And this is my training function. Training XGBoost takes the files that I want, create a progress bar, create my training data and test data, create my set, and then use my training algorithm for my classifier, and then provide the algorithm. This is what you would actually use if you were using XGBoost on your local machine, right? So let's go ahead and define this particular function. And I'm going to try this function on a smaller data set, about 300 megabytes, right? Provide the XGBoost in this particular file, so it actually will run this. And on a single machine right now, I have this running this on my single machine, which is about 16 cores or something, and it's just using all those on a single machine. I'm not distributed, and I'm just trying to see what my 300 megabyte file looks like. So I got my time taken about 8 seconds, and I got my validation error, which is low. And then I'm going to use the same thing with the 3 gigabyte file on my machine. Now I'm not going to run it because it's going to take about 133 seconds. But I just ran it before the meetup, and I'm using the same algorithm just with a larger data set. It took about 133 milliseconds. So why don't we do the same thing with the XGBoost Ray? Now, the XGBoost array, the difference between the local XGBoost array and the distributed XGBoost array is that just 3 lines of code that you actually have to change in your XGBoost array to be able to use the distributed array, XGBoost array on the cluster. One is you import the XGBoost array, which is our version of array dmatrix. Dmatrix is the XGBoost version of it. This one is the distributed version of it. We will take your data and then distribute it across the cluster. We have a training function, and then I have an additional class called array parameters. And array parameters are the one that dictate how parallelizing do I actually want those? How much parallelism do I actually want for my training function? And then I use the XGBoost array distributor to actually fan out all the training across that. So what it does is it takes my data and shards it across each and every worker. I have a tracker. It uses, it computes all the tree-based, it computes all the gradients, and then uses tree-bait and rabbit to synchronize the gradients, because when I'm doing the training, I have to figure out, what's the, what GPU is running what gradient, and eventually I have to synchronize that. So the workers communicate that using the Reddit protocol to synchronize that. And so now here's my XGBoost version of it. I'm using the same parameters. All I'm doing is I'm just changing this particular code where I've imported that. I'm using the same data that I'm using, except that I'm using my array data matrix over here. As you can see, this is my array data matrix. And the only additional argument that I've given over here is my array params. And array params over here, you'll see I'll define that in the next function. So now I'm going to define this particular function. And now I'm going to go ahead and execute this. Now, this is what happened at this point. It will go across the cluster and start executing it. So my array param is, I want 8 actors, right? Remember, I told you actors are a way we are actually defined. So you're going to create 8 actors, and I'm going to use 16 CPUs per actor. So it's going to use whatever node that I have. I'm going to use all those for that. So I'm just going to go ahead and start executing this. And at this point, what's actually happening over here, it's going across the cluster. And you can actually see these are all my different ranks. If I have GPUs, then I'll do the synchronization over here. And it's actually getting all these tasks in parallel. So if I go over here up at the top, and I look at my dashboard on my cluster, you can actually see all these are sort of executing. Wow, it's done. Can't believe it. Yeah, so it finished in about 14 seconds. And you can see that it actually used 8 actors to do my training, and it just took 14 seconds, right? And if I were to do this on my local machine, I probably won't be able to do that, right? Even though just this particular local one that I use, it took about 133 seconds just on a small data file. If I did the same thing over here, this would take a very long time. So this was done over 8 actors, over 8 machines, over just within about 14 seconds with the same kind of error rate that I got. So that was sort of doing the training using XGBoost. And it was very simple. All I had to do was specify how much parallelism I want by providing the particular parameter, and it actually went and did that. The second thing we're going to do is we're going to do the tuning, right? And this is what I think Christine or whoever asked is can tuning be used with any other supervised or unsupervised learning? Well, we are doing supervised learning. We're using XGBoost to do our hyperparameter tuning, and we're using distributed tune to tune our XGBoost model. Well, how do you do that? Very simple, right? Just import my tune. I set some parameters. This is my config space, right? This is my regular array hyperparameter tuning, and I'm saying use this particular tuning config space to tune my hyperparameter for the XGBoost. Here's my ETA, my learning rate. Here's my subsample. This is the depth of number of trees I want to go ahead and tune it. The parameters that I'm using for parallelism, I'm going to use two CPUs. I want 8 actors. And if my actor stops for some reason because of the failure, I want you to be able to restart it at least once, right? And then I'm just giving it to tune. And all I do is give the particular function with XGBoost train. I'm giving the files that I need, the parameters, the parallelism that I need, and I just run this particular puppy over here. So what's happening over here is this, now it's fanning across. So you can see that I'm using 62, I'm using 144 CPUs, all 136 of them are busy churning away. And if I go to my Ray dashboard, you can actually see all these are now running in parallel across my cluster, right? And as they are running, they're reporting it back. They're reporting it back to the scheduler to say how many of them are running, how many of them have been terminated, how many of them have been early stopped because of the Ray scheduler. And this should probably take about, yeah, it should be done. So this is where the communication is actually happening. I've terminated 2, which means that I'm done with that, or I've terminated because I don't think I need to run the trial on it. And this is where the massive parallelism happens. You can actually see as I'm going along, the number of CPUs being requested is small because some of the tasks are already being finished in parallel. And as they go, they drop down the CPUs, and I can reuse them again for some other tasks. So I'm at about 34 CPUs currently. I've got 2 tasks running, 6 have been terminated because I started 8 of those actors, each running all 16 CPUs at the same time. And I should be done momentarily. So I got 1 running and 7 terminated. And let's see how the dashboard is doing. Yeah, we can see that we're almost done with all the tasks. We have a couple of stragglers which are still running. And I should be done, right? So this took about 101 seconds to do. If I had to do that on a regular machine, it'd probably take me a few hours to do that. I got my maximum hyperparameter tuning that says this is the best model parameters I got for this particular model. So you can actually use that. So that was the second load that I actually showed that you can actually use XGBoost Ray to distribute your hyperparameter tuning. You don't want to do that on local machine, which is going to take too long. But if you do that on a Ray cluster, I'm running on an Anyscale cluster, but this could be a Ray cluster running on AWS or on Kubernetes or on GCP. So that was the second workload that we are doing. The third workload that we normally do is inference, because once you build a particular model, you actually want to do the evaluation, you want to do a trial, and you want to do that with a large data set, right? So first we're going to do that on a regular machine, which means that it's on 1 node, and I'm going to use 11 gigabyte of file, and I'm going to go ahead and run it. Because of time constraints, I want to give some questions. What I'm going to do is, if you run this, I just ran this before the meeting, it took about 11 seconds, right, for the inference to do that on 11 gigabyte on 1 machine. If I do the same thing with XGBoost Ray, the only difference is that I'm using the same, I'm just using Ray Databricks as Ray dmatrix as my data store. I'm giving the number of actors that I want for inference, and then I'm just going to run it in parallel. And this should take about maybe a 1/10 of the time. This is about 10 times faster than the previous one. Yeah, so it took about 8. So this took about 80 seconds, and this took about 8. So about 10 times faster when you actually use XGBoost Ray on a cluster rather than running on a local machine. And the results are no different. You actually got the same classification for these. Anything above 5 is 1, anything below 5 is 0. You got the same thing. So what we did over here is I showed you a couple of things, that you can use, you can train your machine on a local machine, but it doesn't fit because of the scale. You need that. You can run training across the cluster. Hyperparameter tuning is a very common workload that people actually use. You can actually use Ray's tune to distribute that. I showed that how you can actually do that both on a local machine as well as across the cluster. And you saw the merits and the difference between how tune can parallelize all these different trials and use the appropriate search and schedulers to be able to efficiently stop bad trials. And then inference was pretty straightforward. You do inference on a local machine, or you do it on a server, or you do it across the cluster, whereby you actually get a fairly good throughput and latency. So that was, in a world, my demo. I'm going to open up for questions you have. I know I threw a lot of stuff your way, but more than happy answer any questions that you might have.
Rajiv had a question about Plasma Store not working on Windows. Is that true?
Yeah, so I wouldn't say not working. Windows is something that we are still in beta, right? Because first, obviously, we wanted to make sure that it actually works on Ubuntu, because that's what people are actually using in the cloud. So that was the first thing, and then the second order of thing, we actually want to make sure that people who are running laptop locally are using Windows. So Windows right now, Ray is in beta. We also now have to support M1, right? Because people now have got ARM architecture. So, you want to be able to use your GPUs, because why would you actually buy an M1 machine if you can't use the GPUs? So we have actually released a version of that, and that's actually in beta. But Windows is actually in beta right now. But everything else, you can actually run. So if you have your laptop right now, you do a pip install. On M1, there's an instruction how to actually do the pip install for M1 as well. So yeah, you can run it on Windows, but it is a bit still in beta. I mean, I was doing a tutorial at PyCon, and one of the guys was having a hard time getting things to run, and asked him, "What are you running?" Because they're running Windows. I go, "Sorry, so we can't do much with that." But yeah, I mean, a lot of people are using the Windows laptop as a client for Ray, right? They wouldn't use that to actually run the cluster.
Any other questions, folks?
Any other questions? How many people? I mean, we can probably just put it on the Slack. How many people have heard of Ray? Okay, Tommy Gozzi.
Right.
I've heard of him. Yeah. Thanks a lot, Tommy. Thanks for that thumbs up. I like it.
Here's another question from George. Great session. Any next tips on how you could run a Ray project on the cloud?
Good. How do you actually run project on the cloud? So it is a broad question, and you got many answers to it. But I like the way you posed it. Is how do you actually run a Ray project in the cloud? It touches on many things. What is the develop experience of Ray on your laptop and on the cloud? And I think typically the way I do it is I start everything on my local machine. And I'm not much of a notebook user. I normally use a PyCharm or Visio. And I write all my code. I make sure everything is actually working. And then when I actually want to somehow test it on the cloud or put it in the cloud, there are a couple of things you do, right? Ray has the ability to now run things locally and connect it to the cloud. So when I do a ray.init over here, we don't see ray.init, but actually when you do ray tune, it underneath calls ray.init, which connects to the cluster. You can provide in ray.init where your cluster, where your head node is, like the IP address and all that. If you're running on Anyscale, you just provide the URL, and it's going to directly connect to that, and then submit the jobs to the head node, and now it's actually running in the cluster. So that's one way to do that, right? The other way is that Ray actually has the ability to take your .python files and do a Ray job submit. So you actually create a particular job and you just submit to the cloud. And it's going to run that in the cloud. So in Anyscale, we actually have this thing called job services, where you can actually create these jobs, which actually run for an amount of time on the cloud. And run, what does it run when you take a bundle of .py files and you package them and say, here's my .py file. And when you run that using from your local machine ray.submit, it's going to upload all the local directories or any runtime environment that you provide. So the runtime environment is a way for you to say, for this particular job that I'm going to run on my cluster, I want you to be able to do pip install of these particular libraries if you don't have it on the cluster. I want these libraries to be uploaded from my local file. And any other requirements you actually need, for example, Kanda install, or you need some other packages that can be packaged as part of the runtime environment and you just actually run. Some people just create a Docker image and then just use the Docker image to submit to run it on the cloud. So there are different ways to actually sort of have your job run in the cloud. But the best experience that people get started is first they start running on the local machine, and then they use Ray client to connect to the AWS, to connect to the Ray Anyscale seamlessly. And now things are actually running, and you can actually go to Anyscale to find out, for example, what jobs are running, what this particular Jupyter notebook is actually running on my head node. As you can see, I can go to my dashboard to actually find out. I can go to Anyscale to find out what my services are, what jobs I've submitted, and so on and so forth. So if you're running on an AWS, then obviously you would just create your cluster on your AWS account or on a GCP, and then in your Ray init client, in your .py file or in your Ray charm, you just provide the address. I want to connect to this particular cluster, and now everything is actually running locally. So any Python, any tasks, they get pickled and serialized over and stored on the GCS, and subsequently things get picked up by the Raylets, and they get executed and scheduled. So that was a long answer to a very broad question. Sorry. George, does that address your question?
Question there about also from George asking whether
yeah,
you could answer, but about PyTorch and TensorFlow, both of them.
Yes. So both PyTorch and TensorFlow can be actually used for deep learning, right? And so the way you do that is that when you're saying I want to train this using DDP, right? So what you do is when you actually create your Ray tune, you provide what backend you actually want to use for training. And the backend training, you can either provide Torch, or you can provide Hortonworks, or you can provide TensorFlow. And what happens at this point is that it's going to use the DTP's protocol to communicate all the gradients. So we don't do the gradients. What we do is we'll create the actors which will run your training functions. And the code that you actually write, the PyTorch code that actually does DDP communication, that's actually done by the Torch. So if you're using PyTorch to do distributed computing, then it's going to use the DDP protocol, whatever that protocol is, to communicate between the workers that we actually launch, and it's going to do that. Same thing with TensorFlow protocol, and same thing with Hortonworks. We would just launch the Hortonworks workers, and the Hortonworks workers would run in parallel, updating their gradients to the parameter server. So yes, you can use any of those three backend algorithms, and RayTrain is the one that actually supports all those three. You're a Ray fan, brilliant, love it. You made my day. Who was that? Oh, George, brilliant, yeah. Connect with me on Slack or whatever. You have my the slides. Tommy and Jeff, these slides. Can I just send you the PDF of the slides and you can share with the rest of them? Is that okay?
That's great.
Okay, brilliant. Yeah, I'll send you the PDF, and then you can just share it with the people, because there's a lot of information over there. I have links in there that allows you to do that. Yeah, definitely, George. Join our Slack channel, and I'll be more than happy. And join our Meetup. Give us a star. Any other question? Or even come to the summit. Right, even come to the summit. That'd be brilliant. Yeah.
More Ray. Majid's got a number of questions here.
Oh wow, love it. Okay. Ray specific. Is the wire format the same as the plasma store format? Good question. So the wire the way the thing is actually stored, if you actually create an arrow object, then we're going to use the arrow serialization to store that. If you're actually creating a Python object to put it in the plasma store, then we're going to use the Pickle 5, Cloud Pickle 5 way to actually store that. So depending on which object you actually create. So if it's a NumPy array and you're actually creating a PyArrow data, then we're going to use PyArrow, because that way we want to maintain the consistency of the serialization. On what basis are workers distributed over nodes? On what basis are the workers distributed over nodes? Oh, the workers are distributed. Okay, so each and every worker depends on the number of cores you have, right? So one way you can either minimize or maximize the number of workers you actually want is that when you do array.init, you can actually specify the number of cores, number of CPUs you actually want, or number of GPUs you want. So what will happen is that it will create a number of If you say number of cores, number of CPUs is 4, then it's going to create 4 workers. If you don't specify, then it will figure out how many cores I have, and it will create those worker processes. So there's a difference between worker nodes and the worker processes. Worker nodes are dictated by your YAML file in how many clusters you want to create, right? So if you want to say, I want 16 nodes, and in my head node, it looks like, let's say you're doing it on AWS. So my head node, I want you to be using image this particular file with 16 CPUs. I want that much kind of memory. And that's going to be part of a YAML file. And so when you say, array up, it will go ahead and connect to the array cluster and we're going to create the cluster. So if it's got 16 nodes and each of those nodes has 12 cores, so when you write your array client, when you say array.init without specifying number of CPU, it will create 16 worker processes, each dedicated to a core. Let's see, that was the second part of the question. In general, array related, is it possible to get an agreement on APIs, especially the DF API Spark has, Koala, Dask has, DF, Array has modern. There's also GPU DFs. Okay, one thing I want to make unequivocally clear here is that Ray doesn't have the notion of data frames. Ray is not built on a data frame. Ray is built on this abstraction, right? What you can actually do is you can actually create, you can use Ray, you can use modern on top of Ray to be able to sort of distribute your pandas across, right? So the Koalas is the pandas version of Spark. Modern is the Ray version that you can actually do that. So Ray does not have a data structure called data frame, right? So he doesn't have that. So that I wanted to actually make that pretty clear. Same thing with Dask. Dask is sort of built on bags and data frames, right? Ray is not built on any data structure, right? Ray sort of is built on the compute infrastructure that gives it the abstractions to be able to write this distributed application. So I hope that answers the question. Is it too much to ask for one compute system to handle relational SQL, graph, arbitrary programming language constructs? Is Spark technically obsolete? Oh, that's a politically hard question to ask, given that I come from. Is it too much to ask if for one compute system to handle SQL? Well, let me put it this way. There are different workloads for Spark and the different workloads for Ray, right? If I were to answer that question in a more diplomatic way, if my grandmother asks me, what's the difference between Ray and Spark? And I would say, well, grandma, you got 2 children. One is Julie and one is Jules, right? Julie is very good at doing things that Jules isn't, and vice versa. So in other words, Spark is extremely, extremely powerful to do workloads and data processing and building ETLs and building data lakes. If I was doing data processing, if I wanted to build massive data lakes, I would use Spark. I would not use Ray, because that's not what it's suited for. If I have an SQL load, I would not use Ray. Ray is not suited for that, right? If I was doing massive ETL data processing, I would not use modern on Ray because it's a different workload. I would use Spark. If I was using reinforcement learning, I wanted to do massive distributed tuning and training, would I use Spark? Not necessarily, because the workloads are different, right? Ray is suited for that, so I would actually use Ray. If I wanted to do distributed training at a massive scale and inference and serving, would I use Spark? No, I would use Ray because it's actually meant for scaling those loads. So I think that a very, very two complementary distributed system that happen to have very common roots, which happen to evolve over a certain amount of time, but they came from the same crucible of people who actually worked at RhymeLab and RiceLab, but they're extremely, extremely complementary and they work well, very well with each other. You can run Spark on Ray, by the way. Is Spark technically obsolete? No, it isn't. It never will be. It'll take a while. Yeah, I mean, Spark is there. I mean, Databricks, look at Databricks. They're just like flourishing like crazy, right? Delta Lake is there. So no, it's not. It'll continue to be there. It's probably by de facto the best data processing engine that I have worked with, and I've had the immense privilege and pleasure to work with the original founders and creators of those for 7 years. So I would never say anything like that. Why array distributed compute approach best suited for ML workloads in comparison to other compute-heavy tasks like data processing? I think good question. Good question. I think some of the data processing tasks are very much sort of static graph centralized way of executing the tasks. Machine learning tasks and machine learning folks have very irregular workloads, right? So they could actually have workloads that just take very quickly. They have workloads that actually take a little bit of time, and they have different requirements and resources in the duration of the task. So it lends very well to reinforcement learning workloads or hyperparameter tuning workloads, because all the computation and the graphs are dynamically executed, because you want to get the results right away. Even though they're done asynchronously, you do get the results to figure out what am I going to do next. Whereas if you look at data processing or SQL workloads, they get built over a period of your entire data frame transformation, right? So if you have a large SQL data frame transformation, you're going to do transform this, aggregate this, sum this, and then you're going to call an action, right? So when you go to an action, what happens, example of Spark, is that it's going to create a particular DAG for you. The DAG will go through the SQL analyzer. The SQL analyzer will go through the optimization to say, okay, how can I actually rearrange this particular code so I can get, I can divide them into stages, and then I can do what we call a shuffle across that. And then finally, I'm going to aggregate the data and return that. Well, that actually takes a while to actually do that and execute that, which is very suitable for evenly distributed tasks that actually run. So when you're doing massive data processing in parallel, you'll probably see that most of the tasks are evenly executed across the Spark cluster. So they have this even time of execution. There's no irregularity. The only time you will have this irregularity when you actually have a data skew, but that's mainly because the way you actually have partitioned the data, right? Which is different from ML workloads. They have a very irregular workloads that depends on resources available, that depends on certain tasks may require, say, GPUs. So you want to be able to say, for this particular task, I want to use this kind of GPU. For that particular task, I want a CPU. That is not something that is a property of, say, an ETL job. I hope that answers the question.
Okay. All right, with that, I think we got to wrap it up. Thank you, Jules. It's been a very educational and very interesting. So thank you for your time.
Thanks a lot, Jeff, and thanks a lot, Tommy, for inviting me. If you have an in-person event, let me know. I'll just have to find a way to get to DC again.
All right, sounds good, Jules. Thanks.
All right, cheers.
Bye, all.
Thanks, Jules. Bye.
Welcome.